Welcome to the session 4 of Unit 1 in Digital Signal Processing. In this session, let us try to understand the sampling of analog signals. Before going towards sampling of analog signals, let us try to understand the sampling theorem. Actually, the analog signal is interfaced with the digital computer via A to D converter, that is ADC. ADC consists of sampler and quantizer, and when any signal is to be sampled, we should know its frequency contents. Now, let us see the sampling theorem. When a band-limited signal with bandwidth W is sampled with sampling frequency greater than or equal to 2W, it's possible to reconstruct estimate of original signal from its samples. The sampling rate of 2W is called as Nyquist rate, and the sampling frequency is denoted by Fs. The Nyquist frequency is f sub n, that is Fs by 2. When the analog signal is sampled, it's important to select proper sampling frequency. Let us consider the two cases to understand the proper sampling. Let us try to understand the first case, sampling of analog signals, case 1. Let's consider a signal with bandwidth of 10 Hz and let us sample it with the sampling frequency 100 Hz. So this is the analog signal with the 10 Hz bandwidth, and this is the sampling signal with its frequency 100 Hz. Here we can do the multiplication of 10 Hz analog signal with the 100 Hz impulse train signal, resulting into the sampled signal. So this is the sampled signal, and this sampled signal I will get when I will multiply this analog signal with the train of impulse. In frequency domain, we can see the spectrum of 10 Hz signal around 0 frequency. So here, this is the spectrum of the 10 Hz analog signal at plus 10 Hz and minus 10 Hz. For the frequency domain of sampling impulse train signal, we have the frequency components at multiples of Fs, that is multiples of 100 Hz. This is the frequency domain representation of this impulse train. So as this impulse train, its frequency is 100 Hz. In frequency domain, we can have the frequency components at multiples of 100. Means I can have the frequency component at 0 frequency, I can have the frequency component at 100 Hz, I can have the frequency component at 200 Hz. Similarly, I can have the frequency component at minus 100 Hz. Similarly, I can have the frequency component at minus 200 Hz and so on. For the frequency spectrum of sampled signal, we need to convert the 10 Hz analog signal spectrum with the 100 Hz impulse train spectrum. It means that in time domain, you are multiplying, or we are multiplying the analog signal with the impulse train so as to get the sampled signal. So in time domain, we are doing multiplication. That is why we need to convert the spectrum of analog signal with the spectrum of impulse train signal so as to get the spectrum of sampled signal. So after convolution, we will get the spectrum of sampled signal in this way. So you can observe this is the spectrum of analog signal. If we convolve with this middle component, I will get this sample spectrum between or at minus 10 Hz and plus 10 Hz. If this spectrum analog signal, if we convolve with minus 100 Hz, I will get the spectrum at minus 110 Hz and minus 90 Hz. Similarly, if I convolve this analog signal with the spectrum of 100 Hz, I will get the spectrum at 90 Hz and 110 Hz. We'll just bring the spectrum here for the ready reference. Now if I want to recover my signal back, so for this recovery, we can use a filter with rectangular window around zero frequency from -Fn to +Fn. So this is my rectangular window, or you can see it as a filter I'm using from -Fn, that is my Fs was 100 Hz, so my Fn becomes -50 Hz to +50 Hz. So when we pass the sampled signal through a rectangular window, that is low pass filter, we can get the original signal spectrum. So this is the sampled signal and this is the window. If I multiply these two, I will get this recovered signal spectrum. So by using inverse Fourier transform, we can get back the original time domain signal. So this is my recovered signal spectrum. So I can take its inverse Fourier transform and I can get back my original or estimate of original time domain signal. Let us move towards the second case. Now let us consider here that a signal with a bandwidth of 90 Hz, and let us sample this 90 Hz signal with a sampling frequency of 100 Hz. Let's consider this as the 90 Hz analog signal. Let us consider this as the 100 Hz sampling signal. If we multiply these two, that is analog signal multiplied by this sampling signal, I will get this as the sampled signal. In the frequency domain, we can see the spectrum of 90 Hz signal around the zero frequency. If this is my 90 Hz analog signal, its spectrum is at -90 Hz and +90 Hz. Similarly, I can have the spectrum of this sampling signal. As the sampling signal, its frequency is 100 Hz. I can have the spectrum whose components are at zero frequency, at 100 Hz, at 200 Hz, at 300 Hz, and so on. Similarly, I can have the frequency components at -100 Hz, -200 Hz, -300 Hz, and so on. So I will get the frequency component at multiples of Fs, that is multiples of 100 Hz. For the frequency spectrum of sample signal, we need to convolve the 90 Hz analog signal spectrum with the 100 Hz impulse train spectrum. So in time domain, we have multiplied this analog signal with the impulse train. So in frequency domain, we have to convolve the spectrum of analog signal with the spectrum of impulse train signal. So the spectrum of sampled signal will be look like this. If this analog signal, if I convolve it with this center spectral component, I will get these two spectral components -90 Hz and +90 Hz. If the analog signal, if I convolve with the -100 Hz spectral component, I will get the two components, one at -90 Hz, -190 Hz, and another at -10 Hz. Similarly, if I convolve this analog signal spectrum with the spectral component 100 Hz, I will get the spectrum at 10 Hz and 190 Hz. We'll just bring back these spectrums for our ready references. So in this case, in the second case, we can see that the replicated spectral lines overlap with each other in a converged spectrum. So the replicas are not separated, but there is a mixing of adjacent replicas. The signal spectrum around zero frequency has 90 Hz and -90 Hz components. The signal spectrum around 100 Hz frequency has 10 Hz and 190 Hz frequency components. Similarly, the frequency spectrum around minus 100 Hz has minus 10 Hz and minus 190 Hz components. Here, if we use a low-pass filter from minus Fn to plus Fn, that is minus 50 Hz to plus 50 Hz, we will get the spectrum of 10 Hz, which is the Allied's version of 90 Hz. The phenomenon of high-frequency components taking the identity of low-frequency components is called as the aliasing effect. Generally, the high frequencies are aliased as low frequencies.